So let's start. So good afternoon, everyone. Welcome to this November mini-school. My name is Francesco Petruccione. I'm the director of NITheCS, and today I have the pleasure to introduce for the second time, because I missed the second lecture, Shane McFarthing. Shane is a PhD student here in Stellenbosch, and he's sharing some of his wisdom about how to simulate chemistry on quantum computers. And today is the day where we really do that on a quantum computer. Yeah, so Shane, please, you're most welcome. And everybody knows the rule of the game. Please use the Q&A to ask questions, and after the lecture, we can give you the right to ask the question verbally if you so wish to do so. Yeah, Shane, please, welcome.
Thanks. Thank you very much, Prof. So this is the third lecture in our series of lectures on the electronic structure problem. And just to give a recap of what we covered last week. So last week we focused on the classical methods for solving the electronic structure problem. We covered 4 methods. The first was the full configuration interaction method, which is capable of giving us the exact answer for the specific problem that we're considering. And then because the full CI method requires exponentially scaling resources, we then took a look at some more approximate methods that are able to reduce this computational cost while also providing answers that are of sufficient accuracy, or at least that's the goal. So we looked at Hartree-Fock, which was a method that treats the electron correlation in a mean way rather than explicitly considering the instantaneous electron interactions. We just consider a single electron at each time, and we, when we want to take in the effects of the other electrons, we use a mean field approach. So we treat the electron moving around affected by the averages of all the other electrons. But what we saw was that this method is not really capable of capturing the correlation that we're really interested in for this problem. So we took a look at another method called the couple cluster theory. And what this does is systematically build up the correlation in the wave function that we're looking at. But unfortunately, this also has some computational cost that's incurred. So typically, when we build the wave function in terms of the excitations of the different determinants, we have to perform a truncation. And that truncation affects our accuracy, but allows us to compute the method itself. And we then took a look at another method called the selected configuration interaction method. And what that does is it uses a similar method to full CI, but the wave function that we use is actually truncated. So rather than using the wave function containing all possible slated determinants for that system, we try to extract only the slated determinants that are important. And in that way, we can try to make the wave function more compact, and that allows us to perform the diagonalization with reasonable computing resources. But all of that was simply the classical computing components. And in today's lecture, what we're going to take a look at is the quantum methods for trying to solve the electronic structure problem. So if you missed last week's lecture, it's not too much of a problem. Everything that we do today is more or less self-contained and depends more on the lecture 1 materials. So today's focus is going to be the variational quantum eigensolver method. And to begin with, we're going to be giving some introduction into quantum computing for quantum chemistry and how we can use that to try to make our calculations more efficient. Then we move into looking at some quantum algorithms for ground state computing. And we look at the current states of quantum computers and what's available, what the capabilities of these devices are, before finally getting into the real meat and potatoes of today's talk, which is the variational quantum eigensolver algorithm. So just to begin with, as a brief introduction into what quantum computing is. So quantum computers differ from classical computers in that rather than using classical bits, which have a definite state of being either in 1 or 0 deterministically, we have the concept of a quantum bit. And now the quantum bit can exist in either the states 1 or 0 or some superposition of these two states. And also we can have that the qubits in the quantum system can be entangled in some way, so that the state of one qubit is dependent on the state of another. And these two concepts of the superposition and entanglement of the qubits is what gives us this computational power. And this is what we try to leverage when we design algorithms for quantum computers specifically. So if we know what these devices are, then why would we want to use them for chemistry? Well, one of the first proposed applications of the quantum computers is for this type of problem. So it was proposed that in order to simulate quantum systems, we should try to use a quantum system itself, which is represented on a quantum computer. And by doing this, we can try to reduce the computational cost of performing these simulations. So specifically for chemistry, when we take a look at some of the methods that we looked at last week, in general, the number of the computational cost scales exponentially with the number of electrons in the system that we're considering. But when you represent these systems on a quantum computer, we get an exponential reduction in that due to the fact that we can represent this superposition of states on our qubits in the computer. So now, if we know that these computers have the potential of exponentially speeding up the solutions for chemical simulations and stuff like that, then we have to actually design algorithms that are capable of leveraging these capabilities from the devices. So in this lecture, we're specifically focusing on algorithms that are capable of finding the ground states of these chemical systems. And the first one that we're going to take a look at is the algorithm that's quantum phase estimation. Now, quantum phase estimation was devised with the fault-tolerant regime in mind, which are quantum computers that don't have high levels of noise. They might have error correction being implemented, which requires millions of qubits. And what this algorithm is capable of doing is that if we provide a state that has if we provide a state that has a good overlap with the target state that we're looking at, in this case, the target state is the ground state of the chemical system, then we can compute the eigenvalue or the energy of that state very accurately. So the way that the algorithm works is that you have a control register, which you initialize into the 0 states, and you have a target register where you prepare the approximate state that you have. So just the state that has good overlap with your ground state. So what we saw last week was that one such state is the Hartree-Fock state. Even though it doesn't explicitly capture the correlation between the electrons, it does provide us a decently accurate energy. So you could use, for example, a Hartree-Fock state there. And then what we do is we try to encode the phase and amplitudes of our control qubits. And we do that by applying these control unitaries. And in this case, for this application, the unitary is our chemical Hamiltonian, which represents the total energy of the chemical system that we're considering. So we apply these controlled Hamiltonians. We apply the quantum Fourier transform to extract the phase information and record it in a binary representation. And then we perform the measurements. And what this gives us is the phase of the state, and then we can compute the eigenvalue of that state itself. And this is a very accurate method, but the problem is that the devices that we have today are not fault-tolerant computers. In fact, we have very limited numbers of qubits. We have a lot of noise present on the devices, and as a result, they have limited capabilities. And the reason for this is that developing fault-tolerant quantum computers is really challenging. There are a lot of different companies that are investigating, but more placing bets essentially on which type of device is going to be the device that provides us this kind of scalable and powerful quantum computer. And there's ion trap computers, there's superconducting computers, there's neutral atom computers, and all of these technologies are developing and in a bit of a race, and we're trying to find which type of device exactly is going to give us this computational ability that we're looking for. But the current state of things now is that we have devices that are noisy, they're intermediate scale, meaning that they have limited numbers of qubits, and we aren't able to actually implement this quantum phase estimation algorithm on the device, because the noise simply stops us from being able to compute this part of the algorithm. Trying to perform these controlled unitary operations with the Hamiltonian results in circuits that are too deep for the current coherence time of the devices, and noise just severely affects the quantum Fourier transform. And in general, we just can't use this method right now to try to solve the problem that we're looking at, which is the electronic structure problem. So what we instead are going to take a look at is the variational quantum eigensolver algorithm. And This method is an alternative to QPE that's capable of running on NISC devices, and it takes a hybrid quantum classical approach. So we try to combine some techniques from quantum computing with classical computation and also classical optimization in such a way that we can find these target states of the chemical systems. So specifically, we're going to be looking at finding the ground state, and that's the state with the lowest energy. So the way that VQE works is that it has iterations of the algorithm that occur, and each iteration, the goal is to lower the energy of the trial state that we have. And what we end up getting out of this is that we have a way to prepare certain approximate states with certain energies. And because we do this variationally, we know that the answer from the algorithm is lower bounded by the true answer. So we will never go below the expected, well, not the expected, the true ground state energy for that system, which is good for us because it means that we don't have to be concerned about the energy being lower and being unphysical, which is a type of consideration that you have to have when you look at methods like the couple cluster theory. So to give an overview of how the variational quantum eigensolver works, as I mentioned, it works in an iterative way. So we have multiple loops occurring, and the first step will be to prepare our ansatz. And what that is a quantum circuit that represents the trial wave function that we have. So we use a quantum circuit to prepare a state on the quantum device, the quantum computer, and that state represents our approximation of the state that we're looking for. And then what we need to do is we need to calculate the energy of that state, because we use the energy as a marker or an indication of is the state that we're looking for. So for example, if we have the ground state, that's what we're looking for, then what we're trying to do when we do the optimization is lower the energy systematically. So we need to perform an energy estimation so that we can actually just try to perform the optimization. So the second step and the third step are, those two steps together form the energy estimation. So what we have to do is apply the Hamiltonian for the chemical system onto the state that we have by placing certain gates on the circuit. And then we need to perform measurements and compute the energy itself. At that point, we now have a state that's been prepared on the quantum device. We have a measure of what the energy of that state is. And in order to try to lower the state, we use a classical optimizer to update the parameters in the quantum circuit. And it will update the parameters with the hopes of lowering the energy. And then after doing that, we check the convergence compared to the previous iterations to see if there was any improvement. And if there's still an improvement occurring, then we can go back and repeat the process. And what we're doing is systematically trying to improve the circuit that we have so that the wave function that is represented by the circuit more closely approximates the state that we're looking for. So the first step of trying to solve this problem, the specific problem on the quantum computer, is we need to be able to create and represent the Hamiltonian on the device. So as we spoke about in the first lecture, the Hamiltonian represents the total energy of the system. And if we're trying to now solve the Schrödinger equation, we need to have this operator on the device so that we can actually estimate the energy of the wave function that we're looking at. So for quantum computing, we can now formulate the Hamiltonian in terms of fermionic operators. And those are these fermionic creation and annihilation operators. And what they represent are operations that either place or remove electrons or particles into certain orbitals. So if we apply a creation operator at an empty orbital, then it'll be placing an electron there. And if we apply the annihilation operator at an occupied orbital, we'll be removing the electron. So what we're essentially trying to do is model the motion of the electrons in the Hamiltonian and take into account the different interactions between them. And that gives us these HPQ and VPQRS terms. The HPQ are the one electron integrals, and they represent the kind of the core Hamiltonian. So the expression for the one electron integrals is here. And as you can see, it takes into account the kinetic energy of the given electron, as well as the nuclear attraction. So between the electron that we're considering and also a given, between all the nuclei. And these form the one electron integrals. And then we have the two electron integrals, which take into account the interaction between the electrons themselves. And if you remember in our description of the chemical Hamiltonian itself, it was the kinetic energy, the nuclear attraction and or repulsion, and the electron-electron interactions. We have a nuclear to nuclear repulsion term, but we take that as a constant when we apply the Born-Oppenheimer approximation. So at this point, we have a formulation of the Hamiltonian in terms of the fermionic operators. But in order to actually apply this Hamiltonian onto the sum of the chemical system, the quantum computer itself, we have to apply mapping. And that's because when we have all these fermionic operators, they are in the fermion space, and we need to perform a mapping so that we're working with operators in the spin space, which are operators that are actually implementable on the quantum device itself. So one mapping is called the Jordan-Wigner mapping. And what these mappings essentially do is they map the fermionic operators to some series of Pauli operators or spin operators. And what we're essentially trying to do is take these operations and keep the anti-symmetry of them when we represent them in the spin space. And what the Jordan-Wigner transform does is we take a creation operator and we map it to this series of X, Y, and Zs. And these contain information about the occupation of a given orbital, as well as the parity. So these tensor Zs help ensure that our wave function of the operators are still anti-symmetric. And we have the same kind of relation for the annihilation operators. And what you can see is that for every fermionic term that we have here, we end up with two Pauli terms due to the addition and subtraction terms. So if we have our Hamiltonian in terms of the fermionic operators, and we want to now map this to an operator that can be put onto the quantum device, if we use a mapping like the Jordan-Wigner mapping, what we end up obtaining is a Hamiltonian expressed as a linear sum of these Pauli strings. So the Pauli strings themselves are tensor products of different Pauli operators, which are the spin operators. And so the coefficients that we have in the Hamiltonian can be complex valued. So what we have at this point is a representation of the total energy of the chemical system that is able to be put onto the quantum device. Even though this Hermitian operator, it isn't unitary, but it's just that we have it expressed in terms of unitary operators here when we have the I, X, Y, and Z. And this will be important when we perform our measurements of the energy of the state. So the next step, which was really the crucial step in VQE, is the ansatz. So as we've spoken about, the electronic structure problem is trying to find solutions to the Schrödinger equation. And those solutions are specific states of the chemical system. And we are essentially trying to find the wave function describing those states. And when you use VQE, we use this quantum circuit to generate that specific state. So it's a quantum circuit that forms a trial wave function, and it'll give different amplitudes for different determinants in our wave function. And it's represented as a parameterized unitary operator. So if we have our state, psi theta, prepared on the quantum device, this state is generated by applying some quantum circuits to a reference state. So this state needs to be particle preserving, meaning that it can't violate the number of electrons in the system. And a very common initial state that's used is the Hartree-Fock state. So the Hartree-Fock state consists of a single slated determinant where the lowest energy orbitals are occupied by electrons. The way that this is realized on a quantum device is if you have a register of qubits, then the first n qubits, where n is the number of electrons, will all have X gates on them. Because if we start in the 0 state, we need to now switch the states of the first n qubits to 1 to represent occupancy. And then The rest don't have any gates applied to them, so they have all zeros. And we want to apply this parameterized unitary operator to that initial state to generate the trial wave function of the system. And there's some considerations that have to be made when we consider this ansatz. So for example, for the first point is that the ansatz needs to be expressive enough to create the target wave function. And if we look at the space that we're searching through, it's the Hilbert space of the Hamiltonian that we're considering. And what we're trying to do is find the state in that space that has the lowest energy when we're doing the ground state search. And our ansatz basically forms a search function through that space, and it needs to be expressive enough to generate the target state. And kind of conversely to that is that an expressive circuit can often be very deep or complex. But in this case, when we're doing VQE, we're trying to not have circuits that require too many gates, because as we discussed earlier, the quantum devices that we have now have limited coherence time. They have a lot of noise. We can't have very deep circuits on there. So we're kind of trying to do this trade-off of having an ansatz that's expressive enough to give us the state that we're looking for, but it also can't be too deep. Otherwise, you won't be able to implement it on the device without having the result be destroyed by the noise. So one very commonly used ansatz is the unitary couple cluster ansatz. And this builds on the couple cluster theory that we discussed last week. So as we mentioned, couple cluster theory suffers from scaling issues, and it isn't variational. So the way that you kind of perform the couple cluster approximation is that we ended up with a series of coupled equations, and we then solved those equations to try to find the amplitudes in the wave function. And due to the way that we solve it, it's not a variational method. And as a result, it's not lower bounded by the true energy of the state. So we can end up overstating correlation energy, and we can end up with states that are actually not physical. And if you're trying to perform applications for like real world applications, which is the whole purpose of this chemical simulation, getting answers that represent unphysical states is not helpful. So what we try to do instead is we build on a lot of the methods of couple cluster theory, where they try to systematically include the correlation, but we make the cluster operator unitary so that we can implement the ansatz on a quantum computer. So if we consider the design of the ansatz, just to go back to the couple cluster theory, we have this ansatz, which is the exponential of this cluster operator. And this cluster operator represents the sum of some excitations that we define. So they can be single excitations, which involve moving an electron from one orbital to another. It can be doubles, where we move pairs of electrons around the system. And it can go up until we're considering excitations where we're moving all of the electrons around at the same time. And the issue with trying to use this type of ansatz on the quantum device is that this is not unitary. So what we need to do in order to be able to implement this is make this into a unitary ansatz that can be actually implemented. And the way that we do that is by forming this anti-Hermitian cluster operator, and then the exponential of this anti-Hermitian operator is unitary. So if we change the form of the ansatz from couple cluster theory, we can obtain a unitary ansatz, and that's what we call the unitary couple cluster. But similar to how we discussed last week, where we have lots of excitations to consider, we have to perform some sort of truncation. So if we have all of the possible excitations, which actually scale exponentially with the number of electrons, we typically only consider up to singles and doubles when we apply this unitary couple cluster on a quantum computer. But now that we have this ansatz defined in terms of the fermionic operators, we need to map it to an ansatz that is realizable on the quantum computer. So similar to how we do with the Hamiltonian, where we apply a mapping to take the fermion operators to the Pauli operators, we do exactly the same thing for the operators in the cluster generator. So if I just go back to the Hamiltonian expression, if you remember from couple cluster theory, our excitations are represented in terms of these annihilation and creation operators, because if we move an electron from one orbital to another, we need to apply an annihilation operator to the orbital where we're moving the electron from, and we need to apply a creation operator in the orbital where we're moving the electron to. So we define our cluster operator in terms of these fermionic operators, and then when we apply our Jordan-Wigner mapping, we get this the ansatz in terms of these Pauli operators. So we start off with our cluster operator as a fermion, and we get the Pauli representation. And now that we have this ansatz of the exponential, and in the exponents we have these this sum of the excitation terms that are represented in Pauli operators, we have to be able to map this onto the circuit. And we do this using a trotterization process. And I have an example here of what that looks like for a single trotter step, considering a single Pauli word. So we have this sum of Pauli words usually, and for each Pauli word, we create a circuit block. And we need to consider the specific Pauli operators that make up that Pauli string, because we need to perform basis changes on the circuit to rotate the basis into the one that we're considering with the specific operator. So the positions of the operators correspond to positions of the qubits in the circuit. So for example, the first operator, the X, is for the first qubit, the second one is for the second qubit, and so on. And we have the possible Pauli operators that we can have here is the identity, the X, the Y, and the Z. So each one has a rule for how to do the basis change. So for X, we apply a Hadamard gate. And for the Y operator, we do a rotation around the X-axis by pi by 2. And if we had Z, we wouldn't do a basis change because that's just the computational basis, which we're already in. And the same thing for identity, we don't do anything. So now we do our basis changes, and then in order to encode the phase information of the excitation to make our wave function still anti-symmetric, we have this ladder of C0 gates that go from the first qubit that's non-identity to the last qubit that also doesn't have identity operator. And this encodes the phase, and then we do the rotation around the Z-axis by the parameter that was specified. And then we just have to undo this and rotate the basis back to the original basis, which was the computational basis at that point. So you end up with a circuit block like this for each Pauli string in the ansatz. And now you can kind of see why, if we have a lot of excitations that are being included in the wave function that is created by the ansatz, we can end up with very, very deep circuits. So we typically try to perform a truncation to the singles and doubles level, where we're just only considering single and double excitations. So we've considered the Hamiltonian and how to prepare that for the chemical, how to prepare the Hamiltonian for the chemical system on a quantum device. We've considered the ansatz, which we use to represent the wave function of the system. And then now we need to be able to measure what is the energy of that wave function that we prepared. So the reason we want to do this is we want to see whether our state that we've prepared is a good or a bad approximation of the target state that we're looking for. And we need to perform measurements on the QPU to estimate the energy. And the energy is represented as this expectation value of the Hamiltonian with respect to the state. And as I mentioned earlier, because VQE is a variational method, this expectation value is lower bounded by the true energy of the ground state. So in order to perform the energy estimation, we use a kind of a cycle. Because our Hamiltonian is composed of a linear sum of Pauli strings, we have to do the same process for each Pauli string in the Hamiltonian. So the first one is to process the first string from the Hamiltonian, and then we apply this Pauli string to the circuit. So after we've prepared the ansatz on the device, it'll be first the initial state, which we'll use the Hartree-Fock state. Then you have the whole quantum circuit for the ansatz, which prepares the actual state that we're considering at that point. And now we need to perform measurements afterwards. And when we consider a single Pauli string from the Hamiltonian, we will apply basis changes to each qubit so that when we perform the measurement, we're measuring in the correct basis. So if I go back to here, our Pauli Hamiltonian is expressed as a linear sum of these specific types of Pauli strings. And when we perform the measurements, we need to perform the basis changes that correspond to that string. So if we're going to measure qubit 0 in the X basis, we need to apply a Hadamard gate so that when we do our measurement, it gives us the result in the X basis and so on. So we do the same types of basis changes that we do when we create the actual ansatz. And at that point, what we've done is we've done the basis rotation and we're ready to do the measurements. And now we perform the measurements on the quantum device. And the output of this are binary strings. So strings of ones and zeros representing whether the qubit was occupied or unoccupied. And the reason it's just the 1 or the 0 is because of the collapse from the superposition. And then we need to map those binary strings to strings of 1 and -1 due to the eigenvalues of the computational basis. So if it's a 0, it goes to 1. And if it's a 1, it goes to -1. And what we essentially do is we perform that transformation from the zeros to the ones. And now we have a string of 1 and -1. And we can compute the average value. So when we perform measurements on the quantum devices, we don't just take a single measurement. We take maybe typically thousands of measurements in order to compute an average. And what you do is you take the product of these ones and -1s, which gives you either 1 or -1 as the result. And then we divide that by the number of shots that we took to get an average. And we multiply it by the coefficient of that specific term in the Hamiltonian. And that gives us the expectation value for that specific Pauli string. And we just then add that to the expectation value that we've computed so far. And what that gives us is the expectation value of the Hamiltonian with respect to the state when we do it for every single Pauli string in the Hamiltonian. So at that point, what we have is a measure of the energy of the state that we've prepared on the quantum system. And now, in order to improve the trial wave function that we've prepared, we need to give that energy to a classical optimizer. So as I mentioned in the beginning, VQE is a hybrid quantum classical method. What that means is that we have the quantum computer to prepare the wave function, and we use a quantum computer to then measure the energy of that state. And then we use a classical optimizer to improve the state. And we do that by changing the parameters in the quantum circuit. So the goal with the optimizer is to find the circuit parameters that produce the lowest possible expectation value. And the options for the optimizers that we have is kind of limitless. You can use any optimizer that's capable of performing a minimization. And what we're trying to do is trying to just lower the energy of the state. So once we've prepared the state, we calculate the energy. We then try to lower that with the optimizer. And the whole point of it is to just produce, in our case, the ground state. But the really important part is that, as I mentioned, because the VQE obeys the variational principle, we can just try to keep lowering the energy of the state without worrying about ending up with a state that isn't physical. Because of the fact that it's lower bounded, we know we can just try to keep lowering it with the optimizer and hopefully end up at that true lower bound. Otherwise, we end up with an approximate state that's prepared on the quantum device. And to kind of tie that back into what we're trying to do with solving the electronic structure problem, we're looking for specific states that we can do analysis of the properties of the chemical system in that state. So once we've prepared our approximation of the target state on the quantum device, we can now perform the analysis of different properties, and you would do that typically using the reduced density matrix, which you can prepare from that state. Another strength that we have from VQE is that it can run on NISC hardware. So the QPE algorithm would give us a better answer, but as we mentioned, it's just not feasible to run this on the quantum devices that we have today. So the VQE algorithm is a bit of a stopgap between, to bridge the gap from where we are now to the point where we have the devices that are capable of running a QPE algorithm. And then another thing is that the VQE can also be adapted for non-chemistry applications. So if you can form your Hamiltonian, and then you can apply VQE to find solutions to certain problems or other optimization problems. But there's no free lunch. And if we look at some of the weaknesses of VQE, unfortunately, we can have problems with training the wave function on the quantum device. So the power of VQE is being able to systematically improve the state that you have on the device. And this is completely dependent on our ability to train that state. So the optimizer needs to be able to know how to change the parameters in a way that will lower the energy. But what we find in the presence of noise and with certain types of cost functions and certain types of quantum circuits is that we can end up in a situation where the cost landscape is just completely flat. So we have an exponential vanishing of the gradients, and we end up kind of randomly walking around the Hilbert space with finding certain states, but not systematically lowering the energy. And it's a big problem, and there's a lot of work being done and ways to try to mitigate this, but it just forms one of the restrictions on the application of VQE. Because, for example, when we do the energy estimation, we have to do a certain number of measurements to obtain a certain level of accuracy. And when noise affects the result of those measurement outcomes, then we end up needing to take even more. And to try to avoid barren plateaus, we need to have a very high level of accuracy in the energy that we're computing. So we end up with almost like an exponential increase in the number of measurements that we need to do on the quantum device. We also have the problem of sometimes using circuits that are too deep. So for example, I mentioned the unitary couple cluster ansatz. In that ansatz, you can define the number, like the excitation level that you're going to include in your wave function. But sometimes even for low levels of excitations, we can end up with circuits that can't be implemented. So as you scale up the system size, the size of the chemical system that you're considering, so you include more orbitals and you include more electrons, the number of Slater determinants in your wave function also increases exponentially. And now, when we're trying to consider the excitations that can generate those determinants, we end up with an ever-increasing number of excitations that need to be considered. If we had to implement a quantum circuit that captured all of those excitations, we would end up with a quantum circuit that's too deep to be run on a NISC computer. So these two problems kind of form some of the very, very common obstacles faced by VQE. It's just being able to improve the wave function in training and being able to create a shallow ansatz that's still expressible enough to give us the target state. But in the next lecture, what we go into are some of the developments that have been made in avoiding these obstacles, and also like using an alternative method on a quantum computer to generate that trial wave function that we're looking for that approximates the target state. So that brings us to the end of the lecture. And just to summarize everything that we went through today, we introduced the variational quantum eigensolver as a method for solving an electronic structure problem on a quantum device. We then had an overview of the algorithm and how it works, which showed us that it works in an iterative way. And we broke down the components that make up those iterations. So it's the Hamiltonian, which is a crucial component for estimating the energy. We have the ansatz to represent the wave function of the states and to prepare that state on the quantum device. And then we perform our measurements to get the energy, and we use the optimizer to improve that state on the quantum device. And then lastly, we went over some strengths and weaknesses. And that brings us to the end of the lecture. And like I mentioned, next week, we'll take a look at some of the quantum methods and developments that have been done in order to try to avoid the weaknesses that VQE faces. Thank you.
Yeah, Shane, thank you so much for a great lecture. I think it was difficult to explain VQE in 40 minutes so nicely as you did. And again, I'm always super impressed by the beauty of the slides. So one day you will have to give us a lecture on how to do such nice slides. And you know, as a testament that that your lecture was very nice, without mentioning name, one of us in this room told me that he had to leave after half an hour, but the person is still here. So he probably made alternative arrangements because he didn't want to miss the end. Yeah? I wanted to apologize for the hammering in the background, although I was very happy to hear it because that means that the renovations of the NITheCS offices are proceeding. So that's music in my ear, although maybe it was maybe a little bit disturbing. Yeah? Are there any questions for Shane? And please, the participants online, you're welcome to raise your hand, and we can give you the right to speak. Yeah. There are some compliments in the chat. Yeah. And someone asked Christopher Köhn if we have access to a quantum computer. The answer is in principle yes. Yeah. Through the CHPC, we have access to the IBM cloud. Yeah. At least until March. And I think that the process of extending or giving us access to some other quantum computer is ongoing. Yeah. So hopefully we'll have also in future access to quantum computers. Graham, you have a question. You're welcome to start. Then let me mute myself.
Hi, thanks for the interesting lecture. Just one very basic question. So when on the slide where you had the Jordan-Wigner transform, yeah, you have like a reciprocal operation with x2. I was just wondering what that means.
I'm not exactly sure what the specific of how the Okay, so I'm not exactly sure about the specific parts of this operation, but what I do know is that this one is supposed to encode the occupancy of the orbital, and then the tensor of z's does the parity. So, and it's dependent on the occupancy of the orbitals before that. So I'm not exactly sure about the significance of the operation between the x and the y.
Okay, yeah. So yeah, I don't know, just mathematically, I didn't know whether to interpret it as like an inverse of that operator or if it's something else. But okay, thanks.
And Shane, if I can ask a question, you listed all the weaknesses of VQE.
Yeah.
From a purely practical point of view, what kind of molecules can you simulate on whatever hardware we have at the moment?
Sorry.
Okay,
so if we take a look at, like, for example, we're going to consider an IBM quantum device. So they have devices that go up to 133 qubits, I think, at the moment. So they released their new Heron architecture. And if you try to use VQE for anything close to that, you would run out of money before you got an answer. So they charge $1.60 per second of access on the device. And trying to compute a single evaluation of VQE at that level would probably take days because it requires a really large number of shots due to the noise in the device. I think that the VQE simulations that have been done on real hardware go up to the order of 20 to 30 qubits. Typically what people try to do is if they have a very big system that they're really interested in, but they have limited qubit resources for applying VQE, they'll do an active space selection. So they try to pick orbitals corresponding to certain regions of the system that they're interested in. For example, it might be the part of the system that's close to the other atoms that might be involved in bonding or something like that. And they specifically consider only those orbitals as a subset, and it allows them to reduce the number of qubits. But yeah, at the moment, it's kind of limited to 20 to 30 qubits, which is a system of about 10 to 15 molecular orbitals.
And for curiosity, this morning there was an article in the archive by Microsoft and atom computing, and they claim to have now a 26 logical qubit quantum computer. So that would make a difference.
Yeah. So if I remember correctly, atom computing uses neutral atom quantum computers. And one of the things is that they have really low 2-qubit gate error levels. So as the device fidelities and the noise level decreases, we'll be able to go up in application size.
Any other questions? Omi.
Okay, your last slide, actually the slide before the last slide. Yeah, that one. Can you explain again what is the meaning of sufficiently expressive circuit?
Okay, so when we are trying to create the representation of the target state, we need to be able to include various different Slater determinants in our wave function. So we have Hartree-Fock as one that captures a lot of the energy, but as a single Slater determinant, it doesn't capture the correlation. So what we're trying to do is create a wave function that can include all the different correlation effects. And when you generate that wave function with your ansatz, as a function, it needs to have enough degrees of freedom to prepare all those different components in the wave function. And if you try to make an ansatz that was very shallow, so it was shallow enough to be implemented on the quantum device, you also sacrifice some expressivity because you lose degrees of freedom in your search.
The degrees of freedom here is like the number of parameters do we have, like theta, phi, phi1, phi2.
Yeah.
Okay. It's a trade-off. Either we need to use less parameter.
Yeah, so if we look at like the unitary couple cluster ansatz specifically, the way that the ansatz is defined is we know which excitations are going to be included in the quantum circuit, and you know generally what kind of determinants you can include in your wave function at up to that point. And when we run VQE, what we're doing is solving for the exact amplitudes of the different Slater determinants that make up the wave function. And if you make your circuit shallower, so you reduce the parameters in the circuit, you'll have fewer determinants in your wave function for which you're training the amplitude. So the best case, if you went all the way up, is like full CI, you know, where you have every possible Slater determinant, and when you do the diagonalization of the Hamiltonian, you get the exact amplitude in the wave function of each Slater determinant. With VQE, we're trying to get as close to that as possible without kind of violating the capabilities of the NITheCS device.
Okay, are there other questions here or online? If not, Shane, thank you very much. I see you had lots of compliments in the chat. We'll download it for you as a souvenir. Yeah. And please join us again next Wednesday for lecture number 4, the last lecture in the course, and it will also be the last lecture in the mini school for 2024. Yeah, and then we will start again in February. Yeah. So thank you very much, Shane. Thank you very much for everybody for attending. Thank you very much for DSI for coming in person to check what we are doing. Thank you very much. And yeah, and we'll see you again next week. Thank you. Thank you very much, everyone. Bye-bye.